Dreamers, da 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 da, fighting. Oh, hey there. Oh, what's this? Oh, wrong thing. Wait a second. New measurement fits another piece in the proton radius puzzle. Well, you all know what that means. We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. I must apologize. I changed up my anime music. I was listening to a little flow, doing some Go, the intro from Naruto, like season 4 or something like that. But what are we here for? We're here to try to solve a puzzle. What is that puzzle? Well, the Proton RMS charge radius. What the heck am I talking about? We go to our friend Physics.nist. What do we got here? The Proton RMS charge radius. What the heck is an RMS thingy? That's the root mean square. What does that mean? Well, that's something we had kind of brought up, I think, probably the second time we had talked of that. I think that was on air. I apologize if it wasn't. But basically kind of relating some of the different charge radii and everything. It came out, well, this looks very close to, what was it? Something related to the fine structure constant. I think it is, or at least I'm going to blatantly throw that out here. But basically, the root mean charge is, well, proton's got a positive charge. That's the +1 in elementary charge, even though I think technically it's supposed to be -1, because, Ben, you took a shot in the dark. You had a 50-50 chance. You got it wrong, at least as far as I know. But, hey, welcome, Whitechapel. Welcome. Thank you for joining, my friend. I think things are going to get very interesting very quickly. At least that's my claim. But what is this thing? So basically, you're trying to figure out the charge root. Basically, what's going on here? And mean means, well, you're probably trying to average it. And the square, well, we square things, and we take the square roots of things within physics. Why? I don't know. That's what Professor Carroll told me. I think it has something to do upon the dimensionality or whatever you're working with there. Again, I am not a professionally trained physicist. I'm a dude on the internet that had the privilege of talking with some really smart folks, including some of the folks that are probably watching this video right now. But I digress. All right, so we got some numbers here. And the interesting thing is the proton seems pretty big. It's actually a little bit smaller than the electron radius, because that was what, between 10 to the negative 11 to 10 to the negative 15. This time negative 16. If you notice, we only have a couple significant digits here. What do we got? We got 8.4, 1.4, and that's basically it. We got like 4 digits there. And then we got error of like 19 there. Now, we're going to go to our geometric derivation. So we got the little equation that's on the thumbnail here. This is why I missed a day. I was literally so confused because this, I think, was essentially wrong in one of the posters that I was totally cheating off of Thad for. He had basically minus the zeta function, first derivative of the zeta function at 0. I kept coming with like a y stress zeta. Like, it was so confusing. I'm like trying to do all this research on the zeta function. I'm like, wait, hold on. If basically we have the numbers what I'm supposed to be looking for, why don't I just use the standard method for inquiring into nature? Why don't I just, I don't know, set that as x and see what that comes out to be? And when I got to like 3 significant digits or so, I'm like, oh, it's the Catalan constant. It wasn't the zeta function, because that came out to be something else. And then I actually went back and was listening to the video that we had premiered that I was totally there for, but I totally forgot. And then as Thad, when he edited the video, he actually had the Catalan constant for this equation. So I'm like, oh, cool. I should probably let Thad know to update that in the book if he hasn't already. But okay, what we got here? What the heck is this crazy thing? So in order to figure out the radius of the proton, or its root mean square charge radius, we take the neutron, which we had done in a previous video, which required us deriving the the classical electron radius. So we take the radius of the neutron. We divide it by the radius of the proton. So basically we put x here, because that's what we're trying to solve for. And we said equal to, what is this, k? This is where it gets confusing, because in Wolfram alpha, apparently, the Catalan constant can be represented by k. It's usually big C for me, but I digress. Okay. What happens when we plug this into our friend Wolfram alpha? Okay. We get this thing right here. This is what we have for it. Again, in the previous video, we have the geometric derivation for the neutron radius. And according to the HF8 model, or as Thad would say, the minimal arena, a unity of geometry, call it whatever you would, it's whatever the folks will decide. We get this number, the 7.7255543, yada yada, times 10 to the negative 16. We set that equal to, and the beautiful thing like this, I can just write Catalan's constant in there. So it literally does it for you. It's beautiful. Again, true love, priceless. For everything else is Wolfram alpha. Okay, and get this, and this gives us our result here. It comes out to be a small number. So when we get to 1, comes out to be this. So essentially, it's approximately 8.43. All right. 8.41. You're off. You're off. This again. This is why it's a puzzle. And I was a little hesitant to do this video until I did some extra digging. Yeah, I think you guys are going to like this. But, okay. Get 8.414. An error of 19. All right. So we got 8.434. So if we take that 19 that's in this, that'll bump that up to a 2 with that 1. And then we have the 9, we'll carry the 1. That'd be a 3, and that'd be 3. So it'd be 8.433. We have 8.434. Beams, you're still off. You are outside the error bars. You are correct, my friends. I'm totally incorrect. Now, why might this actually be a good thing? Apparently this is a puzzle. Why do I say this? Again, the links to the articles in the doobly-doo if you want to take a look at this. It's fascinating. Because this is something, it's like, oh, we know the electron does so many more digits. Proton, and even the neutron, that seem to be baffling us. Hydrogen spectroscopy brings a surprise and the search for a solution to a long-standing puzzle. The nucleus of all atoms consists of protons and neutrons, and the simplest of all atoms, hydrogen, has just one proton. The radius of the proton is very small, about 1 femtometer, which is about 10 to the negative 15 meters. That's wicked frickin' small. Smaller than the radius of the hydrogen atom by a factor of 60,000. 60,000. Why? Because the electron has all these orbitals and stuff, and the little tiny, like, kind of crunchy, I'm conjecturing here that maybe it's crunchy, nucleus, that proton, is much smaller. I mean, I wonder why they were modeling them after the solar system and stuff. I don't know. Sun is a very big ball. We're also really far away. It was like 100 million miles, kilometers, something like that. As a proton is such a fundamental particle, much effort is devoted to measuring its size. Since 2010, proton size has been puzzling theorists and experimentalists alike. Measuring transition frequency is an exotic form of hydrogen. Instead of an electron, a muon, an elementary particle 200 times heavier than the electron, is orbiting the proton. A 4% smaller proton size was found. One of the fundamental building blocks of chemistry, apparently, and physics, was found to be a wee bit smaller. I wonder if it had anything to do with the increased mass, because the muon, it's basically the electron's cousin. It's basically the exact same. This is about 200 times heavier, like 204, 207, something like that. Yes. The near 6 sigma discrepancy with both regular hydrogen spectroscopy and result from electron-proton scattering was coined the proton-sized puzzle, and finding a solution initiated intense scientific debate so far without a definite outcome. On page 79, basically they're going through all the fancy stuff there, like some of the doobly-doo. I don't have access because I don't have the requisite thing. The proton radius puzzle. The proton radius puzzle is, again, brought to us by our friends Wikipedia. Take it for what it's worth. Is an unanswered problem in physics relating to the size of the proton. Historically, the proton charge radius was measured by two independent methods, which converged to a value of about 8.77 femtometers. 8.77? You have 8.4. Really? It looks like it may have changed over some time, or at least... Let's just continue reading. This value was challenged by a 2010 experiment using a third method, which produced a radius about 4% smaller than this, 8.42 femtometers. Oh. 8. Oh, that seems to be about what we have right there. Welcome, Gap. Thank you for joining. We're just trying to see if we can't solve some mysteries within our realm of persistence. Again, we're going to need some more experimental data to confirm this, but I'm just saying that, I don't know. If we have the radius of the neutron that we did a couple of videos back, and then we just put x to this, and we set this to k, which is a known mathematical value that seems to be quite fundamental, the Catalan's constant. Let's jump into that. This is going to be fun. Catalan's constant, brought to us by Wolfram Alpha. So, it's that thing here. Again, I know I'm confusing you all. That uses big K. I'm using big C. Just personal preference. And that's what comes up in Wolfram. So it gives us this massive number string of digits. 0.9159, yada. I use like 17 digits or so. That should be more than enough, because we typically, at least Dad likes to use 15 significant digits because he cares about 14, because we all remember, I believe it was Professor Brian Greene that once said, Newton came along and he gave us 7 significant digits for gravity. And Einstein came along and we got 7 more. It's like, really? 7 significant digits seems to be where a lot of our different fundamentals seem to go a little, it's almost like there might be something going on around 7 significant digits. I'm just saying it might explain a lot. So we got this. And Catalan's constant is very interesting because you can have this equal 1/8, the side of the 1. And I thought that was the golden ratio for a second there. That's actually the Lurch constant. Yes, Lurch. But 1/4 and 1/16. Again, these are very interesting constructions. You can get all the fancy maths there. Go to Wikipedia. Mathematics Catalan's constant. And again, here it's G, but we can't use big G because that's Newtonian gravity in Wolfram Alpha, so that's why naming things is very important. It's defined by beta of 2, which equals the infinite sum of n equals 0. So we got 1 raised to the n, and then 2n plus 1 squared. And that's equal to 1 over 1 squared, 1 over 3 squared. So basically we use all the odd numbers and we just keep on squaring them. Comes out to be this number that we know for a lot of digits. We know it now out to, what's that, million, billion. We know it out to like a trillion or so digits. So do we know exactly what it is? I don't know. As long as we got at least about 15 right now, I think we're good. We've known that since, I don't know, 1832, 1864. We seem to get less significant. I don't know. But the interesting thing is, let's take a look at some of its uses. In low dimension topology, Catalan's constant is 1/4 the volume of an ideal hyperbolic octahedron. That's one of the Platonic solids. And therefore 1/4 of the hyperbolic volume of the complement of the Whitehead link. Oh. In knot theory, the Whitehead link, named for J.H.C. Whitehead, is one of the most basic links. It can be drawn as an alternating link with 5 crossings. 5 crossings, they say. From the overlay of a circle and a figure 8-shaped loop. I'm sure must be a total coincidence. We continue. It is 1/8 the volume of the complement of the Borromanian rings. Oh, it's kind of like the Olympic rings there, except it's -2. Now, if only we could try to see a connection between a proton. If only there were 3 things within a proton that we might be able to decipher. Well, that's for smarter people than me. In combinatorics and statistical mechanics, it arises in connection with counting domino tilings. I never had such an appreciation for dominoes, aside from a pizza, until a few weeks ago, when I found out it seems to be integral to a lot of our Roman persistence. Apparently, allegedly, conjecture-wise. Spanning trees and Hamiltonian cycles of grid graphs. In number theory, Catalan's constant appears in a conjectured formula. See, look. If you're not sure, it's okay. You can conjecture. Just be like, I don't know, but what if this was true? Let's take a look at the data. And that's why experiments are more important than ever, or at least precision experiments. We want those great data and numbers because it helps the models. And a formula for the asymptotic number of primes in the form of n squared plus 1, according to Hardy and Littlewood's conjecture F. However, is an unsolved problem, one of Landau's problems, where there are infinitely many primes of this form. Catalan's constant also appears in the calculation of the mass distribution of spiral galaxies. I'm noticing this right as we're going through this, because now that's a good way to jump to our friend Math World. Excuse me. No. This is reference.wolfram.com. Catalan. We got the number and everything there. I'm going to scroll down to something I noticed a little earlier. Distribution, continued fraction, plot range. What is this? List line plot reference. Accumulate stuff and things. The square root of that through 20,000. I'm not saying this has anything to do with how spiral galaxies are formed, but after reading that, I'm like, kind of looks like a dispersion of, I don't know, like a vortex, maybe through something kind of like a fluid. Does this explain more than I am saying right now or inferring? No idea. Again, smarter folks than me are going to need to figure this out. But, let's go back to Catalan's concept just one more time. Just because we like some juicy notes and we want to have further reading, maybe actually cite like more different articles. I mean, don't get me wrong. We'll go back to this in just a second. What is further reading and stuff we should look into? Wikipedia, what do you got? See also, what's this? The Giesking manifold. Double cover the Giesking manifold happens to be the volume of the hyperbolic figure 8 knots complement. How very interesting. Hey, Griswold. Yes, fractal spiral diffusion. Yep, lights. You know what, man? Do I know what all this stuff is? No, not at all. I'm a dude on the internet, but the way I use it, I try to characterize it, is like combinators for noobs, I call it. It's like, all right, you got stuff, it's doing things. So, and if we get computers and stuff, why am I going to try to figure this all out by myself and make my brain explode? Again, it's like, I think human beings working with computers to try to make it a better world, I don't know, if and when general artificial intelligence may or may not take over, I claim they're going to take after us, because we're going to be their examples. If we want to set the example of burning everything to the ground, hey, again, it's going to take after whatever helps develop it, I say, or I claim. If we give them a good example, then we can avoid the Ultron scenario. The means of destruction channel does not promote the burning down of all the stuff and things. Although, I do support the legalization of dueling if it would help prevent that. Consenting adults, consent matters. Also, a list of mathematical constant, and particular values of the Riemann zeta function. I think that's one of those big unsolved problems in mathematics or something. Again, 2023, rumor has it, is the year to see. All right. So let's go back to the thing, because again, this number does not match the code data number. It is out of the deviation by that last one there. Now, the reason why I say this might actually probably not as big a deal is because, remember, it literally just changed by 6 sigma. Why was that? Oh, we got a new precision experiment. Okay. New measurement fits another piece in the proton radius puzzle. It's brought to us by energy.gov. Yes. But, all right. Go through there. What we got here? Okay, let's just read it. Textbook pictures make atomic nuclei seem tidy, but they're actually fuzzy clouds of subatomic particles. This makes it hard to measure the size of positively charged protons in nuclei. Historically, scientists used 2 different methods to get an approximate measure of proton size. The proton radius puzzle arose in 2010. That's when a then new, more sensitive experimental method for measuring the size of the proton by replacing the electron with a heavier muon unexpectedly revealed a value that was 4% smaller than he attained for the previous 2 methods. So, nuclear physicists may now have solved the proton radius puzzle with a unique new measurement of the charge radius using a novel electron scattering technique. Cool. So, it helps better. So, let's get into some of the numbers here. Okay. So, essentially back in the day, we got this number here. What is this number? That's at 8.751, then plus or minus that. So, again, that's a lot different than that. That's how we get to like the 6 sigma difference there. Okay. So, what's the other numbers we have here? Okay. Zoom out. Okay. So, they have this here. Okay. 8.418 and then plus or minus 6. Oh, okay. 0.00067 femtometers. Oh, okay. And then over here, this other one is 8.31 plus or minus, so that it literally could be, I don't know, 9 or 7. We don't really know. So, yeah, again, we're trying to figure this out. We're going to need more experiments, but I'm just saying that at least these numbers over here, 8.434, 8.4, oh, those last 2 ago. I don't know. Again, is this necessarily head-on? No. But you know what? As soon as you start going with a Catalan constant, and it seems to have a lot of connections to other things, you know what? I'll conjecture. My friends, this appears to be a geometric derivation of the RMS charge radius of the proton. 8.431 times 10 to the negative 16 meters. Again, that's just outside over there. We need to change that to a 2, but apparently we're still not quite sure. And if you have something as simple as this, that might be able to explain some things. Is this correct? I don't know. Hey, Sherry, thank you for joining, my friend. But, yeah, this is the thing. We don't know, but I'd say at least utilizing, I don't know, scientific method, propose a hypothesis. Basically I just go into Wolfram Alpha. I'm like, all right, what are the number we looking for? I put that here. I take the other number, I put it there, and I just put X. Oh, excuse me, no. I take this number, radius of the neutron, I divide it to our best measurements, and the number that came out happened to be at least about 3 significant digits of the Catalan constant. I did that on my own, and then I went back and listened to Thad's video. So I was kind of proud of myself. Hey, because that's the thing. It's like, why'd I go to the monastery? To try to learn how to do this so I can actually contribute and not just be like, I'm talking about these things that someone else is doing. Because I'm going to claim that Thad needs help. What type of dude on the internet would I be if I wasn't willing to do it myself? think that's what they call a grifter. Now, I'm totally a grifter. I just try to be honest about it. That's the thing. You do your best. You admit your biases. You make a boo-boo. You admit you were wrong. I mean, how hard is that? It's not like somebody was telling us you can never admit you're wrong. Why? Ego? I don't know. As far as egos go, I prefer French toast. But that's just me personally. But that's all I got for right now. Peace out, everybody. Take care of yourselves. And it's going to be some exciting stuff and things coming up, I claim. Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.